So what happens if I accidentally drop a quick draw? Rock! So, there is this theory that if I get unlucky, a micro crack might form inside the carabiner. That would be invisible to outside inspection. And with repeated loading, this micro crack could grow, and eventually, boom, bada boom. However, there has been many debates whether this microfracture theory is correct or not. So to settle the matter, I visited 3 different companies for this video. I got access to a very advanced testing equipment, even looked inside the carabiners, and had a conversation with metallics engineer from Mammoth.
That's the lowest one we had so far. So maybe it will get interesting.
Maybe it will get interesting, he says. And the results kind of surprised us. So enjoy. So step number 1, we need to make carabiners fall. I was considering to go to some building, but this way we can control the height and I get to play with my impulsive purchase. So a bit of 3D modeling and electronics, and we got this. Opa! Totally legal. Ta-da! I wonder how it's gonna be good.
3, 2, 1.
The sound. Step 1 of this experiment is to clean the lab. It has to be hard surface, you know? Keyboard warriors would complain less or differently. Oh, maybe I should go a bit gentler. And that's 40 meters. Holy shit, it's far up. I would recommend everybody to go a bit away. Okay, ready? 3, 2, 1, go. And that was disappointing. I was expecting that the quick draw will fall like a dart and we'll have a nice smack. But instead it was tumbling like a leaf. More like a parachute, not a dart. So the old genius me thought that maybe the wind from the propellers pushes on the sling slightly and then the quick draw starts. Wee, beep, 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 beep. So change of plans, no slings. Slings don't work. 50 meters.
50 meters.
That's crazy high.
3, 2, 1.
Ooh.
That was close.
And here is the first thing I learned. Most small objects are not aerodynamically stable, so they will not fall like a rock or a dart would. Here is me dropping a quick draw. It immediately flips to the side. Another attempt is to hang it off long string and see if that helps. It's kind of funny. It actually has a lot of lift. Okay. Yeah, it did have a bit of chip here, but I don't know how much that would be a problem. So at this point, it was clear that we needed more weight.
Yeah, but it will not be very consistent.
No, it won't. I gave up on consistency in this experiment.
3, 2, 1.
Holy moly! Okay, now it was Big Bang. Wow, you want to see something funny?
How did that happen?
All of them were connected to this loop. Now, after the fall, this carabiner was here. It managed to unhook from this link and hook to this one and become like that.
That's crazy.
It's like some magician trick.
Okay, so we dropped from 100 meters height and it does not look satisfyingly bad. So maybe we should just... Why are you guys going away? Now it looks significantly worse. Woo, that's nice. Oh. Oh shit, one is a little bit bent.
No, you can't resell it.
Actually, the bent one still works fine. You want this? Leave me a comment and you have a chance to win a brand new carabiner. Actually, never climbed on it, just one day use. So we have a set of carabiners that were dropped from 80 meters on a concrete floor. Then we have a set of carabiners that we abused quite a lot. And then we have a set that I went a bit crazy with. Now for part 2, I am in a very unusual place.
Hi, I'm Andrus and we are at Laba 7. We are a company manufacturing shock absorber and suspension testing, diagnosis and service equipment.
So nothing related to climbing.
We have people related with climbing in the company. I myself also do some bouldering. Okay, Vlad will say that I'm not doing anything, but
Sometimes he's visiting the gym.
Now, to test the theory that with repeated loading, a micro crack could grow inside the carabiner, I needed to find a way how to do thousands of cycles of realistic loading. Unfortunately, most tensile testing machines pull the things very slowly, and then they release very slowly. And that's not what happens in real life. However, luckily for me, these guys had a different machine. Wait, what?
it can kill people easily.
Who, he or the machine?
The operator. Yeah, this is our latest machine.
Latest, greatest.
Inside we have 2 of these linear motors. This is a permanent magnet synchronous motor, which means that the moving part is the coils, not the magnets. And we have the forcer, which is the moving part, and it has the coils inside. And then you have a static magnetic field from the magnets and a controllable magnetic field from the coil. And those kind of push against each other, and that translates into motion.
And translated to human language, this machine can move incredibly fast with super high precision. For example, we can record track data from real rally track and later play it back on this machine. So now this thing is kind of mimicking entire track. Yes.
Something scary, like 6 meters per second or something.
Something scary.
Something scary. You really like these things.
Yep.
2 cycles, you know, high compression, low rebound.
Should I move away from the machine?
What's the worst that could happen is
Here we go.
this.
Imagine a bullet.
Yeah, imagine a bullet, so this can shoot out. So like if you need to
So straight into me, basically.
yeah, well, we can. Well, it shouldn't.
I understood. Even the floor is vibrating a little bit.
I can find you a certain frequency where this thing is just jumping around, and then you'll feel everything.
So that's how you are getting entertained, basically, at work.
Yes and no, but
You can use that as a MIDI player, you know, if you just play the right notes.
What was that?
100 cycles.
That was 100 cycles.
Yes.
Just one beep. What is this red thing on the shock absorber?
Expansion tank.
You have oil here and some oil here. It's also leaking. But when the piston rod is going inside, here you can see how the piston here is moving.
Okay.
When I'm moving here out, gas which is here is compressing piston up.
I thought that once you compress, it will want to push it back against your compression, but it wasn't.
Not
coming
really.
back.
And many people don't understand actually how shock absorber is working. They think that we are compressing something here or something like that. No, we are just moving oils between the chambers. That's it.
But then how does it come back?
You
It
have a
compresses.
spring. Every shock absorber, you have a spring here and it pushes the rod out.
Okay, so basically this just slows down the spring.
Yeah, this slows down the spring both ways.
Ah, here we go. We learned something. So this is our plan. Now, in the past, we did record the forces of the hardest climbing falls, which peaked to about 4.5 kilonewtons to the carabiner. We scaled that up a little bit, removed unnecessary high-frequency data, and this is the load curve that we wanted to mimic for at least 5,000 cycles.
Let's try to replicate the data that you sent me from an actual fall.
Wow, it's crazy how much it's flexing.
Yes, you can actually see the gate rubbing against that notch, which is quite interesting. Normally when you climb and you take a fall, you don't think of something like that happening.
Okay, so now we're gonna take the carabiners that we abused a lot. This one is even bent. I'm actually curious if it's gonna straighten from these loads or no. What's your guess?
It might.
Well, let's fix it. 5,000 cycles done. It's still bent.
Is it?
Yeah, it's still bent. Now, before we brake test these carabiners, I wanted to visit one more interesting place.
Whoa! Okay. Today I'm in another place which is very interesting and we have a lot of stuff here.
Part of their business is industrial high-quality 3D printing, both in plastics and in metal, which is really impressive to see.
And this is like welding, 3D welding. It's high accurate 3D welding with laser.
So you weld humanoids.
We can. These all parts are 3D printing. So we have skull, which is a 3D printing, of course, as anatomical model.
Is this like the real size of the
Yes.
skull? It looks kind of small.
Yes, it's real size. So we have cranial implant, orbital floor implant, facial implant here, and the big temporomandibular joint implant.
Jesus, this is so complicated. Who can design these implants?
We have special software.
This is a 3D mouse that I can feel the thing.
You can feel?
Yes.
Okay, while nerd in me was really entertained, the real reason I came to Smart Factory was this machine.
So many of you worried that there might be a micro crack inside of the carabiner that we cannot see. So now we're gonna try to see.
Yes, computerized tomography. We can scan whatever parts we want. It may be a plastic part, it may be a metal part. We can observe what is inside, that they have cracks, voids, or something like that.
So I was thinking maybe to compare the most abused one and the brand new one and see if there is any difference inside. If there is, we continue. If there isn't, then case closed.
Okay, we will see. It will turn 360 degrees in half an hour, 1801 photo. These images will be reconstructed and we will get 3D volume.
So this is our carabiner, and now you can see layer by layer of it.
As you can see, we can go slice by slice. Slice is 0.03 millimeters, so 30 microns. If there would be a crack, you could definitely see something inside of it.
Yeah.
I just ran through whole part, but I haven't noticed any.
So it's uniformly filled inside.
Yeah.
Good news that we cannot see any imperfections inside the carabiner. So we scanned the most abused one and then we're gonna compare it to the brand new one. More results.
Bam. Here.
Bam.
We can see that the damaged part is bent.
Yeah, it is bent.
Yes.
So what is this? This is like a difference?
Yeah, this is deviation.
Oh, the gate is also very bent.
Yeah.
In the middle it's bent where the hit was actually in this spot.
Yeah.
And the nose is also bent. If this will not show any difference in the final braking strength, then...
Now for the last part, I wanted my samples to be tested exactly as it's defined in the standard. And since I was passing by Switzerland, I couldn't miss an opportunity to visit my friends at Mammut and meet their metallics expert.
I brought some gifts for you, as always. I have all kinds of different samples. This one is my favorite. The question, would you whip on this?
Seeing the bend here, I would not.
It's a little bit bent, okay. You wouldn't whip on this.
No.
No, this is not bent.
No, this one looks okay. But you can see it either, it fell from very high or something, or quite a few times. And the spring of the gate also feels quite loose. I know you did something special to it. It's not like just normal use.
So I brought a lot of samples. Some were brand new as a control group, then a group that we dropped from 100 meters, then one group that we had a lot of fun with, and the final group where we went really crazy.
Let's see if Mammut carabiner, which is rated for 21 kilonewtons, is gonna withstand 21 kilonewtons.
If it's brand new, it will, 100%.
100%. Now there's gonna be a game of not blinking when it explodes.
Yeah.
Jesus Christ.
That was 22 kilonewton.
Wow. Okay, now it's a new carabiner or carabiner, which we loaded for 1000 cycles. Do you think that affects the strength? Like this constant deformation. Do you think that does something to the carabiner, or it's designed to flex?
We don't design it specifically to deform in a specific way or in a specific amount, but on those loads, like below 10 kilonewton, there is just such a margin that it's staying in the elastic deformation of the aluminum, so we're safe as long as you don't go to the plastic deformation.
Now this is actually very interesting. Every metal, be it a carabiner or a spring, can flex, and this is called elastic elongation. However, if we apply more force, we will permanently deform it, and this is already called plastic deformation. And I got curious to find out where is this plastic limit for the carabiners. So stay till the end of this video, because there we will go a little bit nerdy. Alright, so we broke all the new carabiners, and it was clear that such cyclic loading does nothing to the carabiners, at least not to the brand new ones. All of them broke above their rating. So next, a set that we dropped from 100 meters. These mostly had just light scratches, looked similar to what you might see on older carabiners. Only one had a little missing piece.
Yeah, this has a bit of...
Yeah. 23.2 kilonewton.
22.3. 23. So basically dropping from 100 meters makes the carabiner slightly stronger. Good.
No, we cannot say that yet. But
So we broke all the samples, and again, all of them broke above their rating. And ironically, some samples were even stronger compared to brand new.
for now, we only have 2 breaking points, here or there. If one had something like this or a bit deeper exactly here or somehow there, that would have more impact on
So you say that
strength.
there are parts of carabiner that are more susceptible to breaking, and if you have a nick in those parts, it's more problematic.
Yes.
We break either here or here.
Yeah.
So if I would have a nick in that area or close to the nose, that would be more problematic.
Yes.
So now we are looking into a situation like this. Would you whip on this?
I would be scared to climb on this one.
This one has much
Yeah, this is
deeper
quite
cuts, and here as well, a lot of deep cuts.
Yeah.
Now this group of carabiners looked really bad. Personally, I wouldn't be comfortable using carabiners that look like this.
Very abused carabiner
Yes.
without extra load. No way. Okay.
That's the lowest one we had so far. So maybe it will get interesting.
Maybe it will get interesting, he says.
And it didn't. Even though they were braking at slightly lower forces, it was still above their rating, except one sample that was very close.
Not very interesting, but actually very nice to know that even after that abuse and that many cycles, it's still fine. And moment of truth, the last sample. It's bent, it's heavily scratched and nicked, missing parts of it. The gate is also looking sideways. Loaded 5,000 times. He said he would not whip on this.
Yeah, this is the most abused carabiner.
Let's see. It's very interesting now. Let's go! 3 kilonewtons, 5, 6, 7, 8, 9, 10, 11, 12. Okay, super good enough. 16, 17, 18, 19, 20. No way, 21. 22. Look, it keeps going.
Oh my God.
It was the best?
22.5. Yeah, it was one of the best. There's only one that's better. How is this possible?
So we broke a lot of carabiners, and I think we kind of reduced the sales of carabiners for moving on from now on.
Overall, we can say that this abuse you did was
Not enough?
not really enough to really cause a safety problem in terms of braking strength. But then you really have to look into other problems on your carabiner. If you look at this, it's a bit sharp everywhere. That could definitely damage the rope.
So if you do this, you don't need to panic, simply inspect it, and if your carabiner doesn't look like mine did, you should have enough safety margin. Okay, maybe a little note from the future editor me. What we showed is that properly loaded carabiners are incredibly reliable. However, there are still many ways how they can fail. For example, here is Daniel Woods snapping a quick draw. So if you're new to climbing, I highly recommend to watch my belay masterclass video on carabiners, so you would learn how they can fail, so they would not fail on you. Now, before we go to the bonus part of this video, a couple of thank yous. First of all, thank you to Mammoth. They've been sponsoring my channel for a while now, which I appreciate a lot, but more importantly, it's always super interesting to visit them, to learn from them, and then share with you. Yay, thank you. And also, my visits to Laba 7 and Smart Factory was super cool.
Wow, that's crazy. That actually looks really bad. I wonder if my vertebrae are gonna look like that after so much editing.
So if you want to learn more what they do, links are in the description. And now, bonus time. Now, we mentioned that such flexing for the carabiner was not an issue because it was staying in the elastic deformation limits. However, I was still curious to find out what is the force that you can pull on the carabiner before you permanently deform it. So the plan was to pull the carabiners to different forces and observe the elongation.
So now we pulled to 9 kilonewtons and then we relaxed down and it came back to exactly what it was before.
Yeah.
So now we're gonna try to pull to 10 and see, to 11, to 12, until we find when it starts deforming.
Yeah.
So we incrementally loaded the carabiners to higher and higher loads, and here are the observations. At around half of the carabiners rating, we can already see a very slight permanent deformation, but it's only about 50 micrometers, which is not something you're gonna notice. However, that changes quick with higher forces. At 70% of the rating, deformation is already about half a millimeter, which is significant, and pulling to even higher forces, carabiner becomes very plastic.
6 millimeters already. It elongated for 9 point something millimeters, almost for a full centimeter before breaking. Maybe like this. Yeah, this was like full centimeter longer.
This type of carabiner, as long as you stay below 10 kilonewton, it would always go back to the same shape. You would have no problem.
So of course I got curious what happens if you repeatedly load above 10 kilonewtons.
Yeah, now we're gonna pull on the carabiner up to 15 kilonewton, go back close to zero, 15 again, back to zero for, a while.
So after the first pull, the carabiner had almost half a millimeter of permanent deformation, and then repeated pulls were slightly growing that, but less and less on every extra pull. However, this is the behavior on the relaxed state of the carabiner, when it's not under load anymore. If we look at the top of the chart, where we can see elongation under load, it is much more interesting. For the first cycles, elongation keeps growing as well. However, later it starts shrinking, and this is due to work hardening, where metal becomes stronger and harder, but less ductile. Now, in theory, work hardening could lead to stress cracking and compromised strength. So to test this, we pull this carabiner till failure. While normal elongation curve of the carabiner would look like this, after the hardening cycles there was a new elastic limit, and it took more force to deform the carabiner further. However, that had no effect on the final braking strength. Now, of course, in real-life climbing situations, we would never reach those forces or that many cycles, so it's really nice to know that there is such a huge safety margin. But in case you're rigging something where high forces are possible, then keep in mind that our investigation just scratched the surface. Also, 50% of elastic limit or yield limit that we found is for this carabiner. If we would change the shape of it, or maybe how the metal was treated, the numbers could be different. So I hope this metallics world is as interesting for you as it is for me. And if you have any questions, put them to damn comments, because I plan more videos on this damn topic. Alright, now since singularity of stupidity is coming, I'm trying my best to protect my biological thinking apparatus, and lately I've been fighting hard against my mindless dopamine scrolling habits and replacing them with habits that grow new brain cells, like using Brilliant, who is also kindly sponsoring this video. Brilliant is where you learn by doing, with thousands of interactive lessons in math, programming, AI. You can learn what's coming to replace you, and lately I've been enjoying their new data science content. I always find it so beautiful when you can visualize a complex data in a simple way. And the best part is that all the courses are divided into short lessons, so you can spend as little as 10 poop minutes a day to build the habits. Also, their courses are made by world-class teachers and researchers from MIT, Microsoft, Google, and more, who definitely know how dumb we can be, and that's why all the courses always start from ground up, so you don't feel lost. So yeah, highly recommend it. You can try becoming brilliant, or try Brilliant for free for 30 days by visiting brilliant.org/hardiseasy, or click that, or there is a link in the description, and you will also get 20% off their annual premium subscription. Thank you for fighting singularity of stupidity.
Kind of disappointing and very nice at the same time.
It's disappointing that we couldn't show real damage on the carabiner.
Yeah.
But it's good and reassuring knowing that, okay, we have margin.
There is no big like, ba boo, bah. It's just lots of broken stuff and nothing. Enjoy climbing.